Lekana. Lekana is blockchain-based document archive storage that we have built for Pageroonilne cloud-based e-invoicing platform. First, let's look at some background information about the Lekana and motivation behind the reason to build the Lekana platform. So, Lekana is blockchain-based document archive storage for large-scale cloud system. So, let's Lekana platform built for Pageroonilne, which is one of the largest e-commerce employer in the world. So, Pageroonilne plan to use that Lekana platform as their archive document storage. So, let's get bit introduction about me. I'm Erang Bandara. I work as a lead engineer at Pagero Sweden. So currently working with my PhD research with blockchain distributed systems and federated learning research areas. So currently I'm attached with PMAS Virginia, USA. So I'm involved with various research projects, blockchain distributed systems, cybersecurity, machine learning, federated machine learning kind of things. Actually, our main motivation of doing this kind of research is so do research and build some production grade application based on these researches. So actually, that we just not stop publishing a paper. We always trying to build some real world production grade application based on our researches. So Lekana is one such production ready platform that we have built. We have built various other platforms as well, so based on our researches. So since we have background with engineering, that means with the industry as well as with the research, we were able to easily do this implementation. So that's the main thing. Okay. Um I'm on Twitter, so this is my Twitter username. So if one maybe we can contact via Twitter. Let's look at some background information about Pageroonilne. So their business domain and some architecture information. Pagero provides cloud-based e-invoicing solution. It's one of the largest e-invoicing provider in the world. So it has customers around more than 120 countries and handle 200 200k plus documents invoices per day. That means it accumulates 200,000 invoices per day. So Pagero platform built with microservices-based architecture. So it's this high-level architecture of the Pagero Online. There are different services on there. It uses RabbitMQ kind of infrastructure for asynchronous infrastructure for microservice communications. So main thing is Lekana is one microservice in Pageroonilne platform. So which used to store the archive documents. If we talk now, let's talk about the Lekana platform. Lekana platform built for Pageroonilne as its document archive storage. So we mainly targeted to build document archive storage for large scale cloud system. Any cloud-based solution can adapt Lekana platform. In here, that Pagero transfers and handles 200k new documents per day. That means it accumulate 200,000 plus documents, basically invoices per day. So Pagero archives its customers' documents after 2 years. So it maximally keeps customers' documents for 2 years. So based on the customer agreement, after that they archive it. So we built Lekana platform to store these archive document information, document payloads, and build. We have invented a new thing called document hash chain, which used to store in the blockchain. So basically, Lekana platform used to store all this information. Uh, let's look at the Lekana architecture. So this is the high-level architecture of the Lekana platform. There are two major components. So blockchain-based document hash chain storage and document archive document storage. So archive document storage, it contains two parts: storage API and storage DB. So storage DB is the place where actual archive document information, basically payloads, their metadata information, for example sender, receiver, date, this kind of information, all this information is stored in the storage DB. So storage API exposes to API for external microservices, so clients to interact with the Lekana platform. So the main thing is blockchain we have used to maintain the hash chain of this archive document information. We maintain hashes of this archive document as a hash chain which belong to the customer. Each customer has their hash chain of their archive documents, so which maintain on the blockchain storage. So it's archive document hash chain storage. So if we take a deep look at these components, so archive document storage and document hash chain, basically archive document storage can identify as an off-chain storage to the blockchain. We store all the archive document informations and payloads. So then document hash chain, blockchain storage which store hash chain of the customer's archive document. Uh, let's look at some information about the archive document storage. So it has two layers, as I have mentioned previously: storage API and storage DB. So archive document information basically is metadata, sender, receiver, dates, and document payload stored in the storage DB. It can be identified as a off-chain storage of the blockchain. So storage DB can build on top of any distributed database. So we mainly use Apache Cassandra based distributed database to build the storage DB. So storage API exposed to APIs to create, search, and validate archive document and their hash chain to the outside parties. So then other microservices can interact with Lekana platform with using this storage API. So for an example, so for create archive document, so from any microservice or any client can send a create archive document message with document payloads, document metadata to the storage API. So then storage API interact with storage DB and save the document payload and document metadata on there, create archive document on there. Then it interact with the blockchain to create a hash chain record for this archive document. So let's look at the hash chain functions on the blockchain. So archive document hash chain. Lekana platform stores customers archive document hash record in the blockchain-based storage. So the main thing is that these hashes stored per user or customer in the blockchain. Each customer has their own hash chain, which corresponding with the which contains the hashes of customers archive documents. So document hash record keeps a reference to this parent document hash. That's how we model the archive document hash chain. So let's look at how the that structure of this hash chain. So if customer's hash chain, if we take a customer's hash chain, this is how it's look like. So one hash chain record contains ID, custom ID, and parent ID. Parent ID means the last hash chain record of the corresponding customer which saved in the blockchain. Then create time, archive time, payload hash. Parent hash means the hash of this parent document, and total hash. It can get this information and get the SHA-2560512 hash as the total hash. Okay, so when new hash record is created, it search for the last hash record which corresponding to given user customer and adds that record ID as the parent hash. Then calculate the total hash based on parent hash, create time, archive time, and payload hash. In this way, we build customer's archive document hash chain on top of the blockchain. So each hash chain record refers to its parent hash record. So the hash chain based archive is designed for the integrity such that it is not possible to remove a single document from the archive without breaking the cryptographic chain. So that all the archive document modeled with the cryptographic chain. So the integrity check, if some violation happens, the integrity check on the archive hash chain will reveal such actions. So hash chain data in the blockchain can expose to outside parties, for example customers in Pageroonilne, to verify the integrity of the document. For an example, Pageroonilne customers can fetch their archive document data from the storage DB and hash chain of this document from the blockchain. So then they can validate that hash chain against the actual document data fetched from the storage DB and check the integrity check. So if something alteration or any violation happens, so this that this validation can reveal such action. So that's the main goal of having separate archive hash chain on top of blockchain and archive storage on the cloud-based storage. In here, that by storing document data in archive storage, that means off-chain storage, and hash chain data on the blockchain, they can address the common issues in cloud-based data storage. Most of the time, cloud-based data storage, the lack of immutability, traceability, and data provenance. So in here, that we handle all these concerns because that it will give more immutability, because that separate archive hash chain will be maintained on the blockchain. So then it will give more traceability, because that all the events happen to the archive document, maybe create, update, or anything, logged in the blockchain. So we have a separate blockchain audit log, all the audit log of the archive document maintained in the blockchain. So and it will give more data provenance. So we by this way we address most of the common issues in cloud-based storages by integrating uh, blockchain to maintain the hash chain. Okay. Lekana functions. So there are two main functions in the Lekana: create archive document and validate hash chain of the archive documents. So if you look at the create archive document, this how high level it works. So external microservices can send document create message. It create message contains document payloads, document metadata information. So then it comes to storage API. Then storage API interact with storage DB and create an archive document on there. That means create means save payload and archive document metadata on there. Then it interact with the blockchain to create the archive document hash chain. So all these blockchain functions we implement with the smart contract. There are separate smart contract to handle the archive document hash chain. Basically create hash chain records and validate fetch hash chain records. So it interact with the create hash chain smart contract function and create the hash chain record. When this function it execute, it first find the parent hash record of the customer. That means last hash chain record which corresponding for this customer. Then calculate total hash. Then create the hash chain records. That's how create archive document flow works. So next thing is validate archive document hash chain. So validate archive document hash chain contains the customer ID. Basically, the customer ID request with customer ID comes. It first fetch the hash chain of that customer from the blockchain. So then blockchain finds the smart contract find the all the hash chain of the corresponding customer and return to storage API. So then it fetch the actual archive documents corresponding for this customer. Then it validate the hash chain against the actual archive document payloads. So by this way, if any alteration happen to the data stored in here, it can be revealed by using hash chain stored in the blockchain. Like an implementation, we have done a production implementation of the Lekana platform. Uh, uh, we built production ready version of the Lekana for Pageroonilne leasing platform. So in here, that main goal is all 2-year-old document and their payload saved in the Lekana archive storage and protected in the off-chain storage of the blockchain. Um, in here to implement the document hash chain function, we have used the Rahasak blockchain. Rahasak is another work that we have built. Actually, it's based on another research work. It's also production ready blockchain platform we have built. Rahasak is highly scalable blockchain storage which mainly targeted for big data, IoT kind of enterprise scale applications. It produces high scalability and transaction throughput. So this is how the implementation look like. So archive storage, document storage, and Rahasak blockchain. Archive document storage, it has two components: storage API and storage DB. So storage API built with Scala language. So Pageroonilne use RabbitMQ as its message broker. So due to this reason, we expose RabbitMQ based API to in the storage API, which can use other services to interact with the Lekana platform. Then blockchain, so Rahasak blockchain we have used, so it has a smart contract and as a storage. In the Rahasak blockchain, we have a smart contract platform called Applus Smart Contract. The main idea of Applus Smart Contract is Applus Smart Contract support concurrent transaction execution on the blockchain. It built using Scala functional programming with actor-based concurrency model. So due to this reason, so shared nothing architecture on there. So it uses all the smart contract right on top of actors. So then it can produce concurrent transaction execution. So in here that since Rahasak blockchain mainly deal with big data kind of environment, it exposes Kafka based API for the consensus as well as client interactions. That case all the transaction can be submitted to the Kafka. So then transaction will be streamed to the smart contracts. So that's how archive document hash chain built on top of Rahasak blockchain. That's the implementation. So then finally we have done some performance evaluation of the Lekana platform. So we have get the statistics based on these four major areas: transaction throughput, transaction scalability, transaction execution rate, and search performance. So if you look at transaction throughput, so this is how transaction throughput varies on single blockchain peer. We have measured two type of transaction throughputs, that means query throughput and invoke throughput. There are two type of transaction mainly in the blockchain: query transactions and invoke transactions. Query transactions just check the fetch the status from the ledger, but invoke transaction do some update, that means write to the ledger. So in that case, due to this reason, query transaction produce high throughput than invoke transactions. So every peer have some consistent transaction throughput per second. Okay, then we calculate transaction scalability. So it also measured with core scalability and transaction scalability. So you can see that. So core scalability is high, but scalability is less. But when comparing other blockchain, you can see that we with 515 PS we can achieve up to 10,000 transaction uh, per second. In that case, this produce some high scalability. The main reason of high scalability of the Lekana platform is the underlying Rahasak blockchain that we have used. So Rahasak is highly scalable blockchain environment, so which support for high transaction throughput and scalability as well as concurrent transaction executions. So next, transaction execution rate. So we have measured transaction execution rate against the time with different number of blockchain nodes. So here's the one blockchain node when adding 2 nodes, 3 nodes, 4 nodes, 5 nodes. These are transactions execution rate is varies. So against the time, you can see that when increasing number of peers, so rate is also increased. So then another important thing we have calculated. So we calculated transaction submitted rate and transaction executed rate in single blockchain peer. So we have issued concurrent transactions and measure the executed number of executed transactions. You can see that submitted transaction is high and executed transaction is low rate. In that case, there's a that back pressure between submitted transaction and executed transaction. So we will handle this back pressure operations by using Rasa blockchains Kafka based streaming infrastructure. So due to having this streaming infrastructure and back pressure operation handling, so we could easily deal this kind of scenarios. So that's the transaction execution rate and submitted rate. Finally, we have done some search performance. So all the data on the Rasa blockchain as well as Lekana platform exposed with the Elasticsearch based search API. That means all the data can be read via using Elasticsearch. So in that case, we recorded some search throughput. So you can see that. So how search throughput varies against the number of transactions in the Elasticsearch storage, number of records basically. So you can see that with 2 million records to search some data, it took around 4 milliseconds of time. So its main reason is so the power of the Apache Lucene index based Elasticsearch API. Okay, so that's the transaction search related evaluation. So these are the main evaluations that we have done with the Lekana platform. Okay, so then that's it from my side. So if we have any questions or discussions, so we can talk about it now. Okay, then thank you very much for your time.